Sir? Sir? I can't hear you, sir. Anybody can hear me?
Yes, I can hear you.
Okay, so it's the prof. All right.
Now I can hear you, my friend.
Yep. Now I can hear you now. If someone does not submit until 3, since you said that at 3 the Dropbox is closed.
Yeah,
How
well,
that-
we can keep track of the people. We left it open, but we keep track of the
okay,
time.
okay. All right.
Yeah.
Okay, perfect.
And because to prevent any further headache for you guys, we left it open, but we track of the time they deposited.
All right.
Now, can you see the screen now?
Yeah, we can. Yep.
One.
Yeah, just
this one. Okay, good. And let's go back. We mentioned last week that we would like to develop a solution for the problem when the heat is that we cannot ignore the internal resistance. Therefore, the internal resistance is controlling the rate of the heat flow to the material. And in this case, we mentioned we are going to develop a solution for rectangular, plane wall, cylindrical, and spherical coordinate. And if this was visualization, that initially the temperature is here, the time equals 0. We expose suddenly to an environment, the temperature is T infinity. Therefore, we can see how the temperature profile inside the material. As you can see, the temperature is changing from one point to another point, from here to here. That shows the control of heat transfer is conduction through the material, okay? And we developed the technique to do that. We mentioned if we're trying to develop for plane wall, this is the integral, the differential equation. This is partial differential equation because we have two variables, and also we ignore the internal heat generation, G. There is no internal, okay? And we know alpha is function of physical property. And if you look at the table at the end of textbook, you will see there is equation for that. There is a value for this value. They have Cp, K, and so on, but also they give you this component. And we mentioned we are trying to solve this problem for the case that initially the temperature was T0 and suddenly we expose it to environment that is T infinity. Therefore, that the time equals 0, Ti, and we assume that there is a heat transfer, the symmetric, the interior right-hand side and left-hand side are the same condition. And we mentioned this exposed here with convective heat transfer to this side, okay? Therefore, this is convective heat transfer equal the conduction heat transfer at X equal L, and these are the two boundary conditions. Again, if you try to solve this differential equation, partial differential equation based on this boundary condition, initial condition, the solution is only applicable to such environment. Therefore, we mentioned we are trying to change the variable and trying to normalize it. And from here, what solution that we get is a general solution. Therefore, it can be applied to any condition that we mentioned. Therefore, it's not on the November. Here we use non-dimensional term. Non-dimensional term, it doesn't matter what value are there. Therefore, the solution can be applied to any different scenario that we have. Then we mentioned that you can, this is when you're non-dimensionalizing the term here, you can see there are some terms appear, and that those terms we mentioned, there's one of them is Biot number that we discussed before, and another term we call it Fourier number. Again, these are dimensionless heat transfer coefficient here and here. Both of them are dimensionless. This is, as I mentioned, representing the ratio of two resistance to convection to resistance to conduction. And here we mentioned there is tau. This tau again is the dimensionless number and represent a Fourier number. Therefore, now we learn Reynolds number, Fourier number, and BO number. These are the terms that we are using here. Okay, and if you would like to visualize what that means, the term here again we're representing Fourier number, the rate of heat transfer that pass through the system, whatever body that you have, by conduction to amount the percentage of the energy stored in the system. Okay, again, this is represent a physical phenomena. What ratio of heat transfer conducted will store in the system? Okay, therefore, these are the number we mentioned here is representative. You have some heat transfer pass through this system. A portion will be conducted, a portion will be deposited. Okay, therefore, this could be deposited, stored, or could be released as a sink. Therefore, in case of your coffee, more heat transfer goes to the system than conduct here because is cooling down. The temperature goes down slowly. Again, this is math. I'm not going to cover it, but your textbook explained that how to solve this partial differential equation. We normalize it, and we mentioned the general solution is like this. The general solution is a component of x, because this function here is only function of x, and this function is only function of the t. Therefore, we solve this one and this one independently, and we try to find the solution to each of them. And we mentioned the total solution is a product of these two, okay? Therefore, this is represent the total answer to this question. But if you can look at here, we have a number of the variable. We do not know what is A, what is lambda, and what is B. And by putting boundary conditions on, again, I'm not going to cover this part, we end up with the solution. We have a solution here for the case that we have a plane wall. Therefore, this solution, as you look at here, we have a summation term. Lambda n is the eigenvalue of the matrix that we have. And then we have here is Bessel function. Therefore, you can see it's very, very complicated trying to solve this one because n infinity go from 1 to infinity. Therefore, you have to find infinite eigenvalue, okay? That's very complicated process to that. The same thing that we are dealing here with Bessel number, with Bessel function. Again, we have dealing with lambda n is going from 1 to infinity. And the same thing we have a spherical. Therefore, these are the three general solutions that apply to plane wall, to cylindrical coordinate, and a spherical coordinate. Therefore, that's as far as the design or calculation procedure is very difficult to use it. Therefore, they made a sort of a calculation, and we have some simplified solution. Simplified solution when tau, Fourier number is more than 0.2. Therefore, rather than using that summation, if we verify the tau, Fourier number, if it's more than 0.2, therefore we can only use the first term. We can ignore the third one. Therefore, the error is very small. This is an approximation term, okay? It's not 100% true, but probably 90% accurate, okay? Therefore, here, now we have no more summation term here for plane wall, cylindrical, spherical coordinate. We only select first when the first eigenvalue. Again, the condition here is tau, it has to be more than 0.2. Now, where we can get this number, now we have a coefficient of A1 and eigenvalue of 1. These two, lambda and A1, is a function of BO number. Therefore, you go and look at, there is in your textbook, table A 4.2. Write it down here, 4.2. You calculate BO number, and then from there we go to that table and give you the value of A1 and lambda 1, okay? Therefore, this gave you the temperature at any point, X at any point, T at any point, okay? If you would like to calculate the temperature at the center of that wall, this is a simplified solution, okay? For wall, for cylinder, spherical. Again, this gives you at X equals 0. That's why we have a T0 here, okay? Therefore, that gave the temperature at any point. This one gives you the temperature at the center. As I mentioned, again, in your textbook, they provide you the graph that you don't have to go and do the calculation. Therefore, you have an option of using the graph, an option of using the simplified equation. Simplified equation, again, remember, please, when tau is more than 0.2. In that case, we can use that one. If it's less than that, we cannot use it. Therefore, if this one, we can, or you can go and use this graph here. Again, look at this graph. This gave you axis x here. Its x direction give you the Fourier number. The Fourier number, look at alpha is a physical property of the material. T is the time after 5 minutes, 2 hours, and so on. And
Sir?
L is the thickness. Any
Sir?
question, please?
Yes.
Yes, yes.
You said it was table 4.2?
4.2 or 4.3. It gives
Okay.
you that one.
All right. Thank you.
Because my textbook again is old again. I'm using still version number 3. Therefore, this is the thickness. Remember, this is the total thickness is 2L. Therefore, L is half of the wall. Okay, this L. Okay, therefore here is you have half the thickness, time, thermal diffusivity. This thermal diffusivity depends on the material you can find. Then this line, the red line, is represent 1 over BO number. Okay, not BO number, 1 over BO number. Therefore, it goes from all the way 0 all the way to this value. Okay. Therefore, if the BO number is very big, this becomes 0 here. Okay. Therefore, that's good. If you calculate the Fourier number, you go and find the appropriate curve related to your problem, and then from here you find. Look at here, the temperature at the center. The temperature of the center of the wall is give you here. Okay. Therefore, this graph is mid-plane temperature at the center of the wall. Okay. And also you have another graph that you can use this one to calculate the temperature at any point. But to be able to use this one, first you have to calculate the temperature at the center. Therefore, you have to go use the previous figure A to calculate the temperature at the center, and then place it here for, again, is 1 of BO number, and here they give you X over L. L is half thickness. Again, my friend, please pay attention. X is half L here, right here. And X is at any point that you would like from the center to this one. X here is 0. Therefore, X equal L, it means at the surface. Okay? X or L, it means at the surface. This represents the temperature at the surface. Any question? If I'm going fast, let me know, please. And then, now the question here is, again, how much heat has been transferred? Because initially it was the temperature of T, 0 Ti, now put it in environment. Therefore, you would like to calculate how much temperature has been, how much energy has been transferred from the system. These are, again, we can calculate this value here. Again, we be able to visualize it. Initial temperature, it was Ti. You left it there for infinite. Now the temperature becomes the same. Therefore, this is the maximum heat transfer. Initially, it was 10 degrees. You place it in the room, the temperature is 30 for infinite. Therefore, you can calculate how much energy has been transferred, mc delta T. But if you would like to calculate at any time, you can use this equation that you have. This is the maximum heat transfer. It means mc T infinity minus Ti. This is the maximum energy transfer because initially it was Ti, now it's in T infinity. Therefore, you know this value, you know this value. You know the lambda from the table that I mentioned. And from this value here, you can calculate how much energy transfer over a period of 5 minutes, 10 minutes, 15 minutes, 1 hour, okay? Therefore, you have an equation here. Again, they give you equation, or you can go back and use this graph. Therefore, you have also figure C. Figure A gave you the temperature at the center. Figure B gave you the temperature at any point inside the material. And figure C gave you how much energy has been transferred. Again, this is Q max. It's mc T infinity minus Ti, and you're trying to calculate the Q. Here is again BO number, Fourier number. If you calculate this value, go up here. Based on the BO number, you can find this value, okay? Therefore, now you have this figure for plane wall. You have this figure for cylindrical coordinate, and you have this figure for a spherical coordinate. The procedure, all of them are the same, okay? All of them are the same, okay? Therefore, we can calculate the temperature at the center, you can calculate temperature at any point, and you can calculate how much energy has been transferred over a period of the time delta T, okay? That's the case. Any question, please?
Sir?
Yes, sir.
the figure C
Yes.
is the total heat transfer?
Yeah, there is. I do not know the meaning of the total. What it represents,
Because you said total.
I mentioned the maximum energy, the total
Okay.
over a period of time. Okay, this is fixed because you know the temperature initial was Ti. If it stayed there for a long period of time,
it's gonna be T infinity.
T infinity. Therefore, this is a maximum heat transfer, and you can calculate the energy transfer at every period of time.
Okay.
And here the time appear right here. Look at here, is here in this number, the Fourier number, you have T. This represents, for example, in 10 minutes, how much energy has been transferred. This T is 10 minutes in this here.
So bi squared tau is equal to the x.
Yeah, you replace here for BO number, they put the value of K, of length, and so on. They put the value for tau, and that's become simplified to this equation. Otherwise, this is BO number. You know what is the BO number, and you know what is Fourier number.
But I was asking, what are the values for the x-axis? What are those values from?
This comes from physical property of the material. Okay, you have a wall made of gypsum board. Therefore, you know the value of alpha for gypsum board, and you know the heat transfer coefficient between wall and environment.
I'm talking about the x-axis. So bi squared tau is the value on the x-axis. Is that right?
That's right. This is the value. That's correct.
Okay. All right. Perfect. That's all I want to know.
Sure. Any question, please? If not, let's do this problem together. You have 5 minutes, please. Read it carefully, try to understand it, and then, because all the physical property has been given, all the dimension has been given, everything has been given, okay? Now, let's look at the first case scenario. Let's look at a sphere. We have a sphere of diameter 5 centimeters. Look at only that part, and then trying to solve it, okay? The question here is, determine how long it take for the temperature of the center of the sphere to reach 25 degrees, okay? Okay, let's see how we can do it, okay? Therefore, the first thing we calculate, we have to see what assumption that we have to make, okay? What do I mean by that? It means but right now we learn two procedures. One procedure that we can ignore the internal resistance. We end up with a very simplified equation, or we cannot ignore the internal resistance, that become complicated one. Therefore, now we have to calculate the BO number. You have the conductivity, you have the length, thickness, and you can calculate, you have H. Therefore, that's the first thing we have to do. Therefore, look at the sphere. We mentioned diameter is 5 centimeters. K is given, rho is given, CP is given. And we know the diameter. The first thing we go and calculate the BO number, okay? And the first thing to BO number, you mentioned HLC. LC, as I mentioned, is characteristic length. And characteristic length, as we showed before, is the ratio of the volume to the area. We know a sphere, and that's the volume of the sphere, and this is surface area. You know, I mentioned 4 pi r square, what we use D. Here we have also D, okay? Therefore, this is the equation that we have for the surface area of a sphere, and here is the volume. We divided the characteristic length. The characteristic length appear in the equation is 0.00333, okay? Therefore, we have H, we have K, and we have LC. And BO number is this one, HLC. LC, again, is characteristic length divided by K. And if you calculate, you can see your BO number is less than 0.1. What that means, less than 0.1. If it's less than 0.1, what that means? Anybody?
The tau is less than 0.1?
No, my friend. I said BO number. BO number.
Oh.
It means it's a lump system analysis?
Excellent. Yeah. Excellent. That means we can use the simplified equation that we have, okay? Therefore, it means we don't need to go through those graphs and so on, and we can use that equation that we had, E to power alpha T, okay? Therefore, we can use that simplified equation, and it means, again, physically, it means the temperature everywhere is the same. The temperature at the surface is the same as temperature at the center. That's the meaning of it. Therefore, we go back and use that equation that we had. And since BO number less than 0.01, the lump system analysis is applicable. Therefore, that's the meaning. It means the temperature at the surface at the center are the same because we can ignore the internal resistance to the conduction. Have you done this page? Can I go to next slide?
Yes.
Yes, sir.
Good then. Therefore, here we can come back and we calculate the B. As remember, that was the exponent that we had over there, and that's the equation that we had. Therefore, if it's less than 0.1, we can use this equation. B is this, if you remember, we call it time constant, and that's what we had it here. We mentioned after what time, that's exactly, we are trying to find out after what time the temperature become 25, okay? Therefore, we would like to know how long it takes the temperature reach 25. This is given. The only unknown here is T. Therefore, we place it here, and we can see after 45 minutes in that environment, with that heat transfer coefficient, the temperature center reach 25, okay? Please ask me if you have any question. Any question, please? If not, let's go to the second one. It mentioned for cube. Let me go back, if you have done. Therefore, they're asking us again for a sphere, a cube of length 5 centimeter. Again, here, we follow the same question here. Determine how long it will take for the temperature of the center of cube reach to 25, okay? Therefore, that's the question here. Again, the same way, we go back. We try to do it for the cube, okay? Therefore, the first thing we have to do, look at, find out the BO number, okay? Again, the BO number, and then we move to calculate the rest, okay? Therefore, in order to calculate the BO number, we need to know the characteristic length. The characteristic length is the volume divided by the area. In this case, become 0.00833, okay? And again, the number is, I believe, should be familiar to you. And therefore, that indicate also in this case, BO number is also less than 0.1, okay? If you do this one, you can see the BO number is less than this one, okay? Now you have verified that again, you can use the simplify approach. It means you can ignore the internal resistance. It means you can use lump analysis method. And therefore, the first thing you have to go back in this equation and trying to find how long it takes the temperature at the center of this cube to reach 25. Therefore, the time is unknown. In order to do that, you have to calculate the B. Again, the B, based on this equation, you have the area, everything here, and then you separate. Any question, please?
Yes, please. What's the E?
Say it again, please.
The E in the equation.
E is exponential. E is a number, 2 point something.
Okay.
Exponential.
I have a question, sir.
I can answer you one question. Yes.
For the internal resistance, it can be always ignored, or?
No, absolutely not. In this case, we calculate the BO number, and the BO number, if it's less than 0.1, we can ignore the resistance. This is the condition. Okay. The only time you can use this equation here, if BO number is less than 0.1. Okay. If it was 0.2, you are not able to use this equation, okay?
Mm-hmm. All right, thank you.
No problem. And for now, we have to calculate. Finish this slide.
Yep.
Okay, good. Therefore, we go to the next slide. Again, we calculate the B, and then we place this equation. Again, B here is that we call that time constant, and that's the value that we have. It's what HAMCP. This is, we can simplify to this number here, and then we calculate the V value. And again, here you can see we reach the same time of 40.55 minutes. And for the simple reason, because the cube and sphere had almost the same dimension, okay? Now the third one, again mentioned, go and look at rectangular premise. It means you have dimension that is given to you. In this case, the dimension was 5 centimeter, 4 centimeter, and 6 centimeter, okay? This is the dimension of this rectangular cube, 4 centimeter, 5 centimeter, 6 centimeter. Again, we have to calculate the value, characteristic length, please familiarize with this term, and then we find that this is the characteristic length that we have here. Again, we go back, the same thing, verify if we can use the simplify equation or not. Therefore, in place you have LC, you have H, you have K, and verify if we can make that assumption. And again, we find this BO number is this one, okay? Again, we can see coincidence, always the same value, okay? Therefore, now we have this value here. Verify is less than 0.1. It means that we can ignore the internal resistance by conduction. We can assume the temperature everywhere is the same and go back, use this equation that we have. In order to calculate this equation, you have to calculate the B value for this scenario and then place it and calculate the time. Please write it down. If you have any question, ask me.
that any point in the surface will reach the same temperature at the same time?
Say it again, please.
Point on the surface will reach the same temperature in the same time?
Yeah, because that's the idea. That's the assumption that we ignore the internal resistance. It means if the temperature at the surface reach 25, everywhere inside the solid is the same. Like you're coming from a traffic jam from downtown, suddenly you end up to highway 40. There is no traffic, you can go fast, okay? That's the same scenario. You have two resistance, one convective outside and one conduction inside. The conductive is controlling the how much energy reach to the surface. When reach to the surface of this cube, everywhere the temperature is, because it's very high conductive material, okay? The conductivity is very high. That's the case, okay? Look at here, we are talking about material. It has conductivity of 429, very conductive material. Therefore, there is no resistance. When the heat reaches the surface, temperature everywhere is the same, okay? If this conductivity it was 20, probably that was not the case, okay? But now we have very conductive material, that's the case, okay? Therefore, now for this scenario, again, we go back and we calculate the value of the B. And here we find this value, and if you place it, after 39.4 minutes, the temperature reach 25, okay? The same procedure, okay? Therefore, now we end up finding a simplified question to solve the problem, and we did it last lecture, and we did it again to be familiar again. The only time we can use that equation, the simplified approach here, if this BO number is less than 0.1. And what that means, it means the conduction does not control the heat flow, the convection, okay? The convection is controlling the heat flow. The resistance to convection is higher than to the conduction. That's the concept behind it. Any question, my friend? Nope. I can move.
Sir, could you repeat what you just said?
I said, do you have any question? This one or before that one?
The convection is...
Oh, convection, okay. When we solve this problem, we made an assumption that when the heat reaches to the surface of the solid, there is no resistance inside the solid. What do I mean there's no resistance? It means the temperature everywhere in the solid is the same. And in order to find that, to be able to find a number to use as indicator, we use the BO number. Therefore, the BO number here represent the resistance to the conduction to the convection. LC over K, 1 over HC. 1 over H it is resistant to convection. LC over K is resistant to conduction. Therefore, here, if this number for resistance to convection is high, this number becomes less. Therefore, the heat transfer comes from here, air, to the surface of the material, one resistance, convection, and then from the surface of the material to the center.
Okay, okay.
Okay, good.
Thank you.
No problem, sir. If you have no question, let's do this problem. Again, it's coming from your textbook, problem number 460. If you have your textbook, open it. Therefore, the number is from your textbooks editions number 6. I give you 1 minute. Therefore, we have a rod, okay, that's a cylinder. And mention here is density is given, Cp is given, K is given, and alpha is represented, this is given to you. The diameter is 10 millimeter, okay, the diameter is 10 millimeter, therefore we have long. Why I said long? What that represent long? When I say long, what that means? Hello, is anybody there?
The heat is going on in one direction.
Absolutely, sir. Therefore, there is heat transfer is only in the R direction. That's meaning excellent. Initially at the temperature of 1000 degree, we would like to cool it down in an environment that the temperature is 25. The temperature is 25. Initially comes from a furnace, the temperature is 1000 degree, come to the room, that warehouse, the temperature of the warehouse is 25 degree, and there is some high convective heat transfer here. Okay, you have convective heat transfer from the rod to the room from this one, and initially Ti at time T equals 0 is 1000 degree. If we leave it to cool down for 3 minutes, I want to know what is the temperature at the center of this rod. Okay, therefore there is a rod is coming out of the furnace at 1000 degree, passes through the belt and comes to the warehouse. The temperature of that warehouse is 25 degrees. The convective heat transfer is 80 watt and so on. I want to know, can I touch the rod after 3 minutes or not? That's for occupational health and safety. We would like to see if what would be the temperature that after 3 minutes. Can I remove it, handle it or not? Okay, what is the procedure? What do you do first? All the physical property has been given to you. K, density. Yes, there.
Find BI.
Absolutely. BI, we call it BO number, okay? Therefore, you calculate BI. And this is a cylinder. What is the BO number now? And BO number is equal HLC, characteristic length, divided by K, conductivity. You have a conductivity, you have H. First, we have to calculate LC, characteristic length. Let's say to save time. Therefore, we make an assumption always. We mention is long. It represents one-dimensional. That's why we use it. We assume all this physical property will not change. Look at here, with temperature change from 1000 to 25 degree. Okay, we assume the physical property remain constant. Okay, this is an assumption we are making. We assume there is heat transfer coefficient everywhere the same. And we ignore the conduction, the losses by radiation, just to simplify, okay? Because the temperature is changing, therefore we assume the temperature radiation exchange is very minimal, okay? This is an assumption. Based on this assumption, we can start to calculate the value. These are, again, the physical property has been given to you. This is rho, this is rho density, Cp, K, and alpha. Therefore, these are the same thing that we given in the problem. Now we go, and let me go to the next slide. We calculate first the BO number. BO number is this one. If you look at the sphere, we can, this is a cylinder, we can calculate, we can see the characteristic length is almost the same as the radius. Therefore, we have this number here. And now we can see the BO number is 0.1. What that means, my friend? BO number is 0.1. Pardon me?
We cannot use the lump system.
I'm sorry for you that you are correct. Now you cannot use lump system. What should we do now?
Go to tables.
And the table, which table, my friend?
The A1.
Okay, no, I do not know what is A1, but
the first one.
Okay, that's the first thing we have to do here is what is the Fourier number? My BO number telling me that I cannot ignore the internal resistance. Now I have an option of using that very complicated equation that is a sigma from 1 to infinity, or I can be lazy to calculate only one term. In order to be able to use the first term, I have to calculate the Fourier number. If Fourier number is less than 0.2, I can use one set of equation. Just be patient. I'll show you what, if you have a short memory, let me show you what that means, okay? Remember here, this was the solution that we had. I mentioned now, we're trying to solve for a cylinder. This is the equation that we have. You have here Bessel function, Bessel function, Bessel function, and all this time here. Therefore, I have to solve all of this to be able to find what is the eigenvalue to solve this one. This is very complicated, and here is from 1 to infinity. It means I need n eigenvalue to calculate this one. Then when we did the calculation, they find that if the Fourier number is more than 0.2, I can be relaxed and use this equation. This equation that you can see has only one term, A1, lambda 1, and Bessel function that we have here, okay? But these values are given to you in the table, 4.2 and so on, okay? Therefore, can you go and use this equation that we have it here, okay? If only the time that we can use this only one term, the first term, if the Fourier number is more than 0.2, okay? Therefore, let's go back. Let's go back to a problem that we had. This one, after 3 minutes, this means here, t is 3 minutes, this one. Alpha is given to us, radius is given to us. Therefore, the Fourier number is 13.61. And I believe it's more than 0.2. Am I correct? Therefore,
Yes,
this is more than 0.2, okay? Therefore, here, tau, the Fourier number, is greater than 0.2. We can use the analytical only one-term approximation technique, okay? Therefore, we do not need to look at all terms because the Fourier number is more than 0.2. Now we go back to one-term equation that we have, but it has a number of constant that we can take it, we can get it from table, I don't know, 4.2 or 4.3, I cannot remember, okay? From there, it gave you the value for this one. Okay, write it down, then I go to the next slide.
Excuse me, sir.
Yes, yeah.
I don't know if I wrote it wrong last class, but I wrote that if the BO number is smaller or equal to 0.1, we can use a lump system analysis. Here it's equal to 0.1. Is that wrong?
Okay, but can we, again, that's a very good exercise, very good exercise. Now, you use this technique and also use the simplified technique to see what is the error between these two, okay? That's very good. Yes, it is mentioned less than 0.1 or equal to this one, okay? Again, it's a very narrow range. Therefore, the best one here, we go through this procedure and we go find out what is the temperature, and then we go and use the simplified equation to see what is the difference between these two. This assumption, how effective it is, okay? Very good, excellent. Therefore, if it's this one, we can use this one. There go to table. Are you finished with this slide, please?
Sir, can you please go back to the slide with the assumptions?
With
The one before that one?
you about the lecture, right?
No, just the slide before this one here.
Let me go before this one. This is the problem here. And then we have this one.
Okay. Constant heat transfer. Okay, perfect, thank you.
And therefore here, if I calculate it and we end up right here. Done with this slide?
Yes.
Okay, I assume yes. Then I go back here and we start to use this expression now. And we can see here that we can use this one to calculate the temperature at the center of the cylinder. Center of the cylinder, okay? It means T infinity, T0 at the center minus T infinity divided by Ti minus T infinity. This is exactly this one. And we have A, we have lambda 1, and then there's one slide here from table 2 BI. These are the value we can get from this one. This is the value from table 4.2, I believe. The addition I have, probably yours the same. These are the value for A1, and these are the value for lambda 1. And we know the Fourier number. We know this one. We know this one. Therefore, this is, again, this is the ratio of TO minus T infinity divided by Ti minus T infinity. Therefore, we replace this one with this one that mentioned TO minus Ti and so on. And we calculate what is the temperature at the center. Temperature at the center is almost 92.5. In less than 3 minutes, temperature dropped from 1000 to 95 degrees, okay? Therefore, now we have some solution. If the problem is a steady state that we did it in chapter 2 and chapter 3, we have an internal heat generation, we solve it. In chapter 4, we came and look at what happened if we assume is transient. It means we cannot ignore, let me just put my slide here. We cannot ignore the energy accumulation in the system, okay? Therefore, all the heat conduction will not go from one side to another side. Portion of that heat conduction will be stored inside the material and will release it slowly on, okay? That we call it transient. It means as a function of the time. Therefore, the temperature change is a function of time. If I change this time in my Fourier number, I can get from 10,000 1,000 slowly as a function of time. Now, therefore, if I want to go, and let me continue this problem, if I want to use the graph, what will happen, okay? This is one behind. Therefore, we calculate the BO number, it was 0.1, right? For this problem. And we find the Fourier number is 13.61. Am I correct? Am I correct?
Yes, sir.
Okay.
Yes, sir.
Therefore, one BO number become 10. 1 over 0.1 become 10, okay? This is 1 over BO number. If I want to go and use the table that we had here, okay? This is the graph, the figure that we have. We mentioned here, x-axis is the Fourier number. It's from 0 all the way to infinity. And here is go from 0 to 1, because this is the ratio. This is your theta at the center, okay? Theta at the center. Rather than using the equation, I can use this figure here. Again, my Fourier number, it was 13.6. It means this is 10, 11, 12, this is 14. Let me go right here. And therefore, that's represent my graph here. Therefore, this line represents 13.6, okay? This line here is, okay? This is 10, 14, this is somewhere here. Again, this graph line, the red one, representing 1 over BO number. And we calculate 1 BO number is equal to 10. It means this line here, right here. Therefore, this represents this one. Wherever they cross each other, I can draw a line here, and go here, okay? That means this line right here. And from here, I can read T0 minus T infinity divided by Ti minus T infinity is equal to 2.78, something like that, okay? Therefore, this is my number. So from here, I can calculate TO. Okay, any question? Therefore, now we have a graph. Rather than doing the calculation, going to use the value table A 4.2 and so on, I can come and quickly use this graph because I know the Fourier number, I have one BO number, and then whenever they cross, I go straight here and read here is TO, the temperature at the center that I'm looking for, minus the temperature infinity, it was 25, 1000 minus 25 is equal 0.75, something like that. Therefore, I can calculate my TO, okay? Therefore, now this is also the graph that you can use to calculate. If I want to go you calculate the temperature at any point, I can go and use table B, graph figure B, okay? That gave me the temperature from the surface to the center, okay? Let me continue this lecture. Any question, my friend?
Sir, I think it was a rod, right?
That's correct. A cylinder.
But this is for planes.
I'm sorry, the same graph. Yes, this. Yes, you are right. You are right, sir. You are right. I have to use a graph for the plane. That's correct. But the same idea here. The same idea. You are absolutely right. I forgot to mention that because I didn't have that for the cylinder. You are correct. You cannot use this one. This is for plane because the one that we have for the rod. You are absolutely right, sir. I'm glad somebody's paying attention. Let me go then. Now let's look at here. So far we assume is long. Therefore, I was able to assume it's one-dimensional. I was only heat transfer coming to the direction of R, okay? But if you look at the can of the Coca-Cola that you're drinking, or Pepsi-Cola, whatever it is small. There's heat transfer from the R direction and heat transfer from L direction, Z direction, okay? Therefore, in this case, you cannot assume it's long because you have also heat transfer here from the top and bottom. Therefore, in this scenario, we have to be able to find a solution that the heat transfer is two-dimensional or three-dimensional or four-dimensional, okay? Therefore, we have to be able to find a way to solve this type of problem, okay? The solution in such multi-dimensional geometry can be expressed as the product of the solution of one-dimensional geometry whose intersection is multi-dimensional geometry. I do not, you have taken the Fourier transfer, right? Laplace transfer, right? If you remember Laplace transfer, we were able to separate this equation to x direction, y direction, and z direction, and then define the solution for x direction multiplied by y direction by z direction, because we were using non-dimensional form. We can do the same thing here. We can assume this small cylinder, the red one, is the product of the long cylinder and a long wall. This represents the plane wall here is long, and this representing this one. Therefore, the solution to this problem is the product of finding the solution for the plane and its infinite cylinder and multiply them together to find for the source cylinder. And mathematically, you have done it before in EMA 243.3, okay? To find the solution for a small cylinder, it is the R direction and X direction. We are separating the variable to X and R, and then at the end, we multiply them together. Now we have a solution to plane ball. We have a solution for the infinite cylinder. Therefore, if I multiply them together, I can find for the short. This is as a function of X, this is a function of R. Therefore, my product is a function at any radius, at any length, at any time, okay? That's the solution to that one, okay? Again, we have done it many, many times in mathematics, okay? Therefore, in this case, we can solve the problem for a two-dimensional by finding the solution in the X direction as a function of, for the plane ball, and the R direction as a function of the long cylinder, and multiply them together, okay? Therefore, in this case, if you have a small rectangular system right here, this is a rectangular system. You mentioned this is the cross-section product of a long plane in the X direction and a long plane in the Y direction, okay? Therefore, for this small case, assume you have a box of frozen vegetable. Is a small box, it's not a huge box. Therefore, you can assume this is a product of a Y direction, long, and X direction. If I cross them together, find for this rectangular system, okay? Therefore, we can solve this top of them by applying the graph that we had. As I mentioned, the figure that we had for a plane wall, for a cylinder, and a spherical together to find for two geometry, okay? Any question, please? Any question, please? Therefore, this is only math. Again, I do not know if you have remember or you have done it or not. If I was trying to solve it for a case like this, two-dimensional, it was second order differential x, second differential equation y. Therefore, I was separating the value as only as function x, only as function y, and then by multiply them together to find the solution. That was the mathematically we used to do it, okay? Now we are using the solution here the same one. Again, calculate for this direction, x direction, and for y direction, and multiply them together to find for the rectangular board that I have here. This is my box of frozen vegetable. I'm trying to find, if I take it from fridge to outside, what is the temperature distribution in the system like this, okay? I'm sorry, I cannot hear you, sir. Repeat it again, please.
It's only 2 dimensions.
It could be 3 dimension.
Okay, if it's 3 dimension, then we have to take the
X, Y, and Z
value for the Z
That's, that's correct. Again, we can use the same figure that we had for X, use it for Y, use it for Z. That's absolutely correct, sir.
Okay, thank you.
Sure. And the same thing that we did for heat transfer, we can calculate for X direction and Y direction and use this equation. I will show it to you by application that we get to that, okay? Therefore, now we have the solution for semi-infinite, we have for long, we have for 2-dimension, 3-dimension that we can apply for any scenario, okay? And we showed this application by solving a problem for different scenario that you'll be able to see exactly what is happening. But the most important thing that you have to at least believe to this scenario, that if I have a short cylinder, I can multiply this. This is mathematically is correct. Mathematically, we have done it in engineering mathematics 232, 235. I do not know the number, okay? Because this one, we had a for 2-dimension dy squared 2, and for x and y direction, we were separating the variable. We solving for x direction, we solving for y direction, and we multiplying the answer together, and we mentioned this is the answer for this, okay? For the mathematics, again, read the textbook or go back to mathematics, okay? Therefore, we can have solve for semi-infinite, for long, for short, for any scenario. We can use the graph that we have, those 3 graphs that we have for plane wall, for cylinder and spherical, and solve for any scenario. Just to give you one example, look at this problem. Again, this number is old textbook, okay? I'm trying to apply this equation with whatever we learn for now here, short brass cylinder. Therefore, this is, we cannot assume long, this is short, it's specifying. And it's specifying by giving us the diameter and the height. Therefore, we can see they are almost the same order of value. We cannot assume it's long. It's 8 centimeter and 15 centimeter. Therefore, this is short cylinder that we have initially is at 150 degree, okay? Initially is 150 degree, and we place it in an environment that start to convect heat transfer at 20 degree, okay? Therefore, we take this one as from the environment that the temperature is 150 and place it in the room, the temperature is 20, and convective heat transfer is 40 degree. What is the temperature at the center of the cylinder? Okay, center of cylinder, it means x equals 0, r equals 0, okay? At that point, okay, at center temperature. And then we come back to here. Therefore, read the problem and try to understand, and I will show you the solution. Ask me, meanwhile, ask me any question that you may have. Any question? Therefore, the first thing here is we have to find out what is the BO number. It mentioned cylinder. Therefore, again, remember, this is short cylinder. If we go back to the solution, we have to solve it for the case we assume is a long cylinder. Therefore, the characteristic length is radius of the cylinder, okay? Remember when you're using this figure that I show you, when you're calculating the BO number and Fourier number, the characteristic length is R, the radius, okay? And for the LC is R. And therefore, I have to solve this problem. I want to calculate the temperature at the center. I have to solve it for a plain wall, and I have to solve this, calculate this ratio for cylinder, and then I multiply them together. Therefore, first, let me look at this case of one I have here, long cylinder. Therefore, the characteristic is R. Therefore, I try to calculate the BO number. This exactly we do here. We calculate the BO number from here. We assumed for the wall first. Therefore, the length is half the thickness that we have here. In L, it means the total thickness of the wall is 15 centimeter to L, but here we are using L. Therefore, we can see the BO number is 0.0027, okay? That tells us something. Therefore, we can go back and use the table 4.2, because we need to calculate the temperature at the center. If you look at table 4.2, coefficient used in one-term equation that we have. And from that table give you the value of lambda 1 and A1. This is when we would like to calculate the temperature, okay? Therefore, we go back here and you can see these are the value for such a scenario that we have, okay? For such a scenario that we have. For such a BO number, table 4.2, I believe in your textbook, give you this one, lambda 1 and this one. And then we use a one-term equation. In order to use one-term equation, we also need to know the Fourier number. The Fourier number is given this one. Remember again, if you read the problem, just a second, the problem mentioned the thickness is 15 centimeter. This is the 2L, okay? Yes, there.
We're not using the lump system because we have both planes. Is that?
We do not know. Again, it's a good question, my friend. It's a good question. Here is again is less than 0.1. You're right. Like I have to use one term, but I do not know in the other direction. Okay, because again I have to calculate both scenario. Okay, therefore I'm following this one. This is the general solution. Therefore that can be applied for even for less than 0.1. Okay, it's a general equation that I'm using. Okay. For this apply also cover the other part.
Sorry, sir.
But again, if you would like to make sure, yes, you can calculate the BO number for X direction, and you can calculate a BO number for R direction. If satisfy both of them, you can use the simplified equation. Here, I just want to show you the procedure, but this you can use also the graph. Okay, you can use the figure that we had. You can use the simplified equation. This satisfy only X direction, I do not know, but probably I should come in immediately to calculate the BO number for R direction. Okay, but here is satisfy here, therefore I can use that equation that I have. Therefore, based on that expression that I have, it gave me the temperature at the center of the wall, long wall, is almost this ratio. This ratio here is 0.812. Therefore, this is, assume if it's a wall, plain wall, long, this ratio is equal to that number, okay? I have to go back and assume it's a long cylinder and repeat all this calculation all over again. I have to calculate this one, I have to calculate this one, calculate here, and then calculate this one, okay? Okay. Any question, please? When you're done, let me know, okay? When you finish writing, let me know. I know you're using picture, whatever if you're writing or taking picture, whatever you're using, let me know.
You take the length at 0.075 meters. It's because it's the half of the cylinder height.
If again, remember when we're talking about the wall, this is I assuming is a long wall, and the is a plain wall. Okay, and if you look at the coordinate that we specify on the figure, we measure the thickness of the wall is 2L, and we need the temperature at the center. That means at X equal L. That means half of the wall. Okay. Let me show you. I just want to make sure that you understand. Let me just go back. Remember how we select our coordinate, okay? Look at here, this figure. Look at this figure here. This L here, your number here, L, is half of the thickness because we assume it's symmetric. The temperature here is the same temperature as here, okay? Therefore, L is half of the thickness. The thickness is 2L, 15 centimeter, and the L is become 7.5, okay? Because we are assuming the wall, both sides are at the same condition, okay? Both sides at the same condition. Okay, therefore we did it for the wall. Let's go for the cylinder again. In this case is 0.01 again, yes. Your number is less than 0.1, therefore I was able to go and use the simplified equation, okay? But I want to just show you this procedure. The procedure is important. Therefore we go back again to table 4.2. Even for cylindrical coordinate, we find A1 and this one. We calculate the tau, and we place this equation here. Therefore, again, look at here, the temperature ratio here in dimensionless temperature here for a long cylinder is this one. And we did the same thing for plain wall, we find this value, okay? And now if you would like to find that for short cylinder it's at the center how much is, you have to multiply these two numbers together. And here we multiply them together. We calculate for the wall, we calculate for cylinder, we multiply them together, and now this gives me for the short cylinder at the center how much it is. And for the temperature at the center of the cylinder is can is 85.6. Okay, let me go back to the previous slide. If you would like to write it down, let me know, okay? Unfortunately, I cannot see your face. Whenever you have done, let me know that I can move to next slide. Any question, please? Are you done?
Yeah.
Good then.
Yes.
If we find this ratio for the cylinder, we find this ratio for the wall, and then we multiply them together to find at the center of the cylinder, short cylinder, at R equals 0, at X equals 0, at the time that we want it, okay? The time we want it, it was this time that we place it here, okay? This time, okay? Right here, after 15 minutes, after 15 minutes, this time, okay? After 15 minutes, the temperature will drop to that one, okay? Now, the second part of the question was asked, the center of the top surface of the cylinder. If you have this can, you would like to find out what is the temperature at the top of the can at the center of the top, okay? The center of the top surface of the cylinder, okay? If it's at the center, R is equal to 0. But now we will look at the surface of the plane wall. The procedure is exactly the same as before. You have to calculate for the center of the cylinder. We did it right here. But now we have to go and calculate for the wall at x equal L rather than x equal 0, okay? Okay, let me know how you're going to do that part. Therefore, if you would like to visually find out what exactly is happening here, you would like to calculate the temperature right here at this point. At the center of the cylinder, but in the top surface. It means at x equal L at the surface, okay? But at the center in line, okay? Therefore, for the plane wall, you're trying to calculate that x equal L, but for the cylinder, you're trying to calculate R equals 0. We already have this one, and we have to go back and try to find the temperature at the surface of the plane, okay? And we had, if you remember, we had an equation that was able to give us the temperature at the exterior surface of the plane, okay? Please, now the assignment number 1 is gone. Project number 1, at least this weekend, spend some time to read and catch up because I finished chapter 4. I do not know if you have started chapter 2 or not. And for now, we have to do this one. Remember, we have this equation. Again, this is come from the earlier equation. If you don't, your memory is like me, let me show you where we got this equation. This was here at the beginning of the lecture. I mentioned we have an equation that gave us the temperature at any point for the plane wall. At any point for the plane wall, okay? There's an expression that we can find here. And this was at the temperature at the center, okay? Any point and the plane, okay? So we can use that equation that we have. Therefore, here we find these numbers from, again, table that we have given. We know the lambda one, we know the A one, we were able to calculate based on the equation that I showed you before. You have lambda one, you have Fourier number, you have L, therefore you can calculate and find out the temperature at x equal L. You can find this ratio. You have this ratio for the surface, you have that ratio for the center. Again, we multiply them together. This was at x equal L. We find this one before at the center of the cylinder, okay? We multiply them from here. Therefore, you know T infinity, you know, TI, you are trying to calculate the temperature at the top of the can at the center. Therefore, that gave you the temperature on the top of the can or the bottom of the can, doesn't matter, because it's symmetric at the center. Therefore, this value you have here, this ratio, this number is given. If you multiply them, you can find the temperature at the top surface on the center is equal 85.6. Okay. Now, write it down if you have any question. Then I do have one question from you.
Sir?
Yes, sir.
So it's the same thing if we want on the cylinder wall instead. We use theta 0T for wall and theta L for cylinder.
Yeah, if you would like to look at the exterior surface of the cylinder outside, rather than calculating here, you have another equation similar to this one that gave you for the cylinder at R equal R.
Yes, okay.
Yeah. Now look at here, just one question. Look at here, we find the temperature at the center. At the center, it was 86.5. And we calculate, we find that the temperature on the exterior surface of the wall on the top is 85.6. What that means? What conclusion you make? You raise it at the beginning.
We could have used
Simplify equation. Yeah,
okay.
because that shows the temperature at the center is almost the same as temperature of the surface. It means the internal resistance, you were able to ignore it. Okay, very good, sir, very good. Therefore, now we have an analytical solution and we have a graph to consider variation of the temperature in solid material as a function of the time. Only for a given geometry, cylindrical, spherical, and plane wall. If the geometry does not have similar shape as this one, then you are in trouble. If you are trying to apply for an egg, egg is not cylindrical, egg is not spherical. Now the question, we have to find a way to solve that problem. Okay. You're putting egg in the boiled water. The temperature will change as function of time. We would like to know what is the temperature story, but the egg is not cylinder, it's not spherical, it's not plane wall. We have to find a way to a solution for such a scenario, odd shaped scenario.
We divide them?
Pardon me?
Can we divide? Consider the
how can you divide? You can divide, what do you mean by divide? You would like to break down the egg
in pieces.
To what? To pieces, then we get in more trouble, my friend. Don't do it.
Okay.
Okay. Therefore, now we find out, okay, we first need to turn on the kit, then let's go back. I want to just get to something else. I will come back to this part. I will come back, but I want to just get to the last page of my presentation. We finish chapter 4. What we have covered here is criteria for lump sum analysis. We are going to do more problem, but I want to make sure that you read chapter 2, 3, and 4, trying to catch up with me, okay? Lump system analysis, we mentioned if B number is less than 0.1, we can use that one, okay? That's the scenario we were able to do some problem. And we make this assumption all the time. We will see it later on again, even when we use numerical technique. We look at also from some defined geometry, transient heat conduction in plane wall, long cylinder, and a sphere. Therefore, we look at, for this scenario, we came up with 3 graphs that we have also analytical solution. The analytical solution can be applied for the scenario that Fourier number. Remember, Fourier number is more than 0.2. If it's not, therefore, we have to find a solution, and that was graphical. And graphical almost, again, is a solution for almost all the scenario. Can be applied to lump, can be applied for even the Fourier number. Therefore, that's, we have to know some simplified equation and some graph and so on. Then we can apply this one also for 2-dimensional, 3-dimensional. If it's semi-infinite or if it's 2-dimensional, multi-dimensional. Therefore, if I have a small little box, like let's say a package of frozen vegetable. Therefore, X and Y and Z are almost in the same order of magnitude. I cannot assume it's long, no. Therefore, we can apply what the solution that we have for 1-dimensional, we can apply that one solution dimensional for 2-dimensional and 3-dimensional and so on, okay? Therefore, this is what we have covered in chapter 4. We did some problem, show you how we can use the simplified equation. We show you how we can use the analytical solution that we obtain for the 2 cases, cylindrical and plane wall. And also we show you also the 2-dimensional for a combination of these 2. Now we come back and we do more problem, but the only time those solving problems good can help you if you catch up and read and try to understand the fundamental behind it, okay? Therefore, technically we finished chapter 4, we finished chapter 2, 3, and 4. Therefore, you have to be ready for the place be able to solve any problem. I send you the solution for chapter 1 and chapter 2, and then we will send it to you to chapter 3 this weekend, okay? Any other question? Any question?
What's the bird's name?
I have no idea. Is it in your house? Who has the bird?
I believe you do.
Pardon me?
I believe it comes from you, sir.
Probably my bird is listening to my lecture and getting excited. They're asking they're asking more questions than you guys are asking me.
That's true.
That's true, my friend. That's good. At least you were able to answer one question. Thank you very much for your time again. And please spend this weekend catching up chapter 2, 3, and 4. And Thursday we solve more problem. But I would like to start chapter 5 because chapter 5 will start to help you to do your project number 2. Okay. Therefore, please do it and try attend the tutorial. If you have any question, approach us. Then we are here to help you. Okay. Thank you again. All the best.
Thank you, sir. Have a good day.
You too. I'm here if you have any question for the next 5-10 minutes. I will be able to answer your question.